Hello, welcome back to a new video. So far, we have only worked with vector spaces with finite dimensions. And the theorems we have seen mostly assume, like, most of the theorems we have seen assume that the vector space we're working with are finite dimensional. For example, in Theorem 7 in section 4.4, the first part of the theorem says that let B equals this list of vectors be a basis of V, our vector space. So in this first part of the theorem, you can clearly see the assumption that V is finite dimensional because the list of basis vectors for V, this list, only has n basis vectors, which is clearly finite. But a vector space can easily be infinite dimensional. And in fact, you have already been exposed to one in section 4.1 when you're introduced to the vector space of all polynomials. And we will denote the vector space of all polynomials as P of R for the rest of the video. This just means that polynomials with real coefficients. So this vector space. So usually in our example with polynomial spaces, we usually require the polynomial to be less than or equal to have a. We usually require the polynomials to have a certain upper bound on their degree, meaning that we usually work with polynomials with degree n or less, or like for example polynomials with degree 3 or less. We usually put an upper bound on the degree of the polynomial, which would make the space finite dimensional. But if we remove that upper bound, we would have an infinite dimensional vector space. And if you try to write down a basis for this vector space, an example of the basis is 1 x squared, x cubed, and etc. So you can see that this list is clearly infinite. But if you put a upper bound on the degree, it usually just cut off somewhere. So you have finitely many basis vectors. So you can see that the list of basis vectors for this space is clearly infinite. Thus, the space is infinite dimensional. Okay. And the reason why that we assume the vector spaces we are working with to be finite dimensional is that a lot of the theorems, in fact, break down when we have infinite dimensions. For example, an example would be the invertible matrix theorem. So a part of the theorem says that if A is an invertible matrix, then this is equivalent to the linear transformation that maps x onto ax is onto. So, okay. So, I will show how this theorem breaks down in infinite dimensions using our example of the space of all polynomials. So, we define a linear transformation T from the space of all polynomials to the space of all polynomials by defining it as multiplying by x squared. Okay. So what this does is that if you plug in, say, x into t, then you get x cubed, right? Or if you plug in, say, 1 into t, then you get x squared. You can see they're multiplied by x squared according to our definition of this linear transformation. Okay, so you can easily see that this is in fact an invertible mapping, because if you say you put some random vector v into through this transformation and you get out, say, x to the 4th power, then you can clearly go backwards until that v is x squared, or you just divide by x squared. So you can see this mapping. So you can clearly see T is invertible. So according to the invertible matrix theorem, the mapping should be onto, but in fact it isn't. So onto, it means that the range of this transformation, so onto, means that the range of T is the entire space. Meaning that you can reach everything. So, meaning that you can reach everything in the space by plugging in some special vector v. So it basically means that so it means that you can TV. So every vector in PR can be reached by T. So TV. So every vector in the space in the range PR can be reached by plugging in some vector in the domain, which you can see clearly isn't true. So you can see here T is clearly not onto, but T is not onto because you cannot plug in some vector v into T and get to, say, 1. So TV equals 1. This is impossible to have TV equals 1. And 1 is a member of the vector space of all polynomials. So you can see here we have a linear transformation T that is invertible, but it is not onto, which is a contradiction with the invertible matrix theorem. So this is an example of how theorems can break down. Theorems in finite dimensional vector spaces can break down when the vector space has infinite dimension. And vector spaces with infinite dimension can be even stranger. Because the nice thing with our vector space of all polynomials is that this vector space has what's called an explicitly constructible basis, which means there is some procedure to generate all the basis vectors. I mean, if you go to if you go to infinity, you'll eventually construct the entire. You can eventually complete the. So if you go to infinity, you can write down a basis for this vector space. You have a procedure to do that. But some vector spaces, so this basis is explicitly constructible. But some vector spaces, some infinite dimensional vector spaces do not have an explicitly constructible basis, meaning that there is no systematic way of writing down the entire list of basis vectors. And one such space is the vector space of all real valued functions, meaning a function that takes in a real number and outputs a real number will denote that vector space as R to the R. Okay. So an example would be, the function, say f of x equals x squared would be in this space. The function f of x equals e to the x would be in this space. Function, say f of x equals sine x would also be in this space. And even like weirder functions like the absolute value f of x equals the absolute value of x, that's also in this space. So you see this is quite a large space, and there is no procedure, because this vector space is so large. I mean, as you can intuitively speaking, if you can imagine it. So this vector space R to the R has no explicitly constructible basis, meaning that there is no systematic procedure of writing down all the basis vectors, even when you say have infinite amount of time, so like the one above. So this vector space has no explicitly constructible basis, meaning that you cannot write down a basis for this space like you did here for this infinite dimensional vector space. And in fact, even if you want to prove that a basis exists for the space, you will need to use the axiom of choice, which you will need to use the axiom of choice to even prove that a basis exists for this vector space. And because infinite dimensional vector spaces are generally, it can get very weird with infinite dimensions, so we generally exclude them in our study of linear algebra. And to properly study them, we usually need we usually need additional structure to properly we usually need additional structure on the vector space to properly study infinite dimensional vector spaces. And the structure can be, say, I don't know, an inner product, for example, or the dot product, on the space, or you can say a metric, etc. So we usually need some additional structure on the space to properly study them. And the discipline that study these infinite dimensional vector spaces is known as functional analysis.